So how do we go about finding the concentration of either hydrogen or hydroxide ions in the lab? So the most common way and the easiest way for us to do this is by doing a lab process we call titration. And this is the lab we're going to be doing next class. So here's the basic idea. Let's say we have an acidic solution, but we don't know how much acid is dissolved in it. If we add a base, the acid will be slowly neutralized. So what we're going to do is we're going to know the concentration, and the amount of base added is equal to the amount of acid that was in the solution to start with. So this allows us to determine kind of the unknown. So let's take a look at example 1. So in example 1, it takes 53.24 milliliters of this concentration sodium hydroxide to neutralize 30 milliliters of hydrochloric acid. So this neutralization problem really is a stoichiometry and a solutions problem. So we have our sodium hydroxide reacting with hydrochloric acid, which is going to produce water and sodium chloride, which is the salt. So this is a balanced chemical equation. You would need to balance this if it were unbalanced. So we now know the reaction that's taking place. We have to figure out how many moles of sodium hydroxide we have. So we have to convert milliliters to liters. So 0.05324 liters and 0.0025 molar sodium hydroxide. So I'm going to multiply those values together, because molarity times the volume in liters will give me moles. So this will tell me how many moles I have. Now notice that the 0.25 or 0.0025 molar sodium hydroxide has two significant figures. So I'm going to want two significant figures in my answer. So I'm going to end up with 1.3 times 10 to the negative fourth moles of sodium hydroxide. So then I'm going to take that value and do a short stoichiometry problem. So I have moles of sodium hydroxide. So I'm going to go moles of sodium hydroxide to moles of HCl. So you can, so in this problem we knew the base's concentration. We're trying to figure out the acid. This is the more common way of doing it, just because making the base is a little bit easier than making the acid. However, you can do it the other way as well. You can know the acid's concentration and determine the base. So this is a 1-to-1 ratio. So then I need to go, once I figure out the moles, I'm done with my problem. So in this case, it's a 1-to-1 ratio. So we end up with 1.3 times 10 to the negative fourth moles of HCl. So because it's a 1-to-1 ratio, my moles haven't changed. So I'm going to take that value. Let's erase this line a little bit. And we're going to divide it by my volume of my hydrochloric acid. So I was told I had 30 liters exactly, or 30 milliliters. So I have to convert that to liters, of course. That's my mistake. So 0.0300 liters. So that will give me my concentration of HCl. So I'm going to end up with a concentration of 0.0043 molar HCl. So it's kind of like the solutions in stoichiometry problems, except we're now dealing with two solutions, which is the most common way of solving these types of problems. We usually don't use the molar mass when we're working with acids and bases because they're usually in solution. So in the next one, we have a different base. We have KOH, which is potassium hydroxide, reacting with sulfuric acid. So we have KOH reacting with H2SO4. So we're going to make K2SO4 and water. Now, right now, this reaction is unbalanced. So I need to put a 2 in front of the KOH and a 2 in front of the water in order to have a balanced chemical equation. So I'm going to do the same exact process. So I'm going to take the concentration of my base multiply it by my concentration of, or my volume in liters, so 0.06581, to determine the quantity of moles of base. So you should end up with 0.00329 moles of your base, which is KOH. So now we're going to take that value and convert it to, so we have moles of KOH. We're going to do stoichiometry to go from moles of KOH to moles of H2SO4. So it's going to be a 1-to-2 ratio. So I'm going to take my value and divide it by 2. And I'm going to end up with 165 moles of H2SO4. I'm going to divide this by my concentration in liters. You'll notice that 30 has 1 sig fig. So my answer will need to have 1 sig fig. My calculator is telling me 0.055 molar, but rounding that to 1 sig fig is going to be 0.06 molar H2SO4. So that would be my final answer. Again, 1 sig fig because the 30 here has only 1 significant figure in it. So the last thing we're going to talk about, which you'll see next class a bit more, I wanted to introduce you to this, is when we do a titration, how can we tell if the solution is neutral? So what we use is we use something called an indicator. An indicator is a chemical compound that turns one color in an acid and another color in a base. There's a whole bunch of indicators out there, and some work better than others. When you do a titration, you're looking for the endpoint of the titration. This is the point where the color of the indicator changes and tells you that you're done. So for the SOL, there's two indicators you need to know. So you need to know litmus and this one, which is called phenolphthalein. I'm never going to ask you to spell phenolphthalein, but that's how you spell it. So phenolphthalein is colorless or clear in an acid and pink in a base. Litmus is red in acid and blue in base. I always remember blue in base for litmus because they both start with the letter B. So phenolphthalein is going to be what we're using in our lab. So this graph right here represents a titration of an acid and a base. So this is kind of logarithmic in nature, so we've been dealing a lot with logs. So if you've seen that before, that's what this would look like. So we have 2 points. We have the equivalence point. This is where the two solutions in a titration are present in chemically equivalent amounts. So you have the same amount of acid and base at the equivalence point. For phenolphthalein, which I'm going to use red, the end point is about right there. So at this point, you're going to see a very light pink color. When we do the lab, you'll see we want it to be as light pink as possible. The lighter the pink is, the closer you are to that equivalence point. So down here below, this would all be, it would look clear. You would not see any of it. So then up here, it's going to be fuchsia or a hot pink. Hot pink means that you're way past that point of equivalence and you cannot use it for your calculations. So for your lab, it is your goal to get a light pink color. What we'll be doing is I'll be walking around when you think you have light pink. I'm going to initial your paper if it's a provable light pink. So we want as light of a pink as possible. And it's good experience for you if you go on to take an AP Science. You'll probably be doing titrations anyway. So it's a good thing to see. So we're going to see this and kind of go